Hi, everyone. My name's Kyle. You're about to watch my talk for the ODSC Data Engineering Conference. I just wanted to explain why I'm not giving the talk live. I really wish I could be there. I love to take questions live and interact with you during the talk. Unfortunately, it overlaps with my company's annual in-person offsite. We only do this once a year, and it's a time for us to come together in person, and I do need to be there for a session for the offsite. Otherwise, I would be giving this talk live, but unfortunately, in this case, I had to pre-record it. I did list my email and Twitter handle at the end of the talk. If you do have questions or you want to chat with me, I'd love to get in touch, but I won't be able to take questions live as usual. Sorry about that. I hope you do enjoy the talk and the rest of the day at ODSC, and I hope to connect with you another time. Hi, good morning. I hope you're all having a great time at ODSC Data Engineering. I'm Kyle Kirwan. I'm the CEO and co-founder at Bigeye, and I'm here to talk to you about reliable pipelines and high-quality data, but without the toil. So to talk about reliable pipelines, let's start by creating an imaginary pipeline. So this starts with obviously our users or our customers, people who are generating our data, and they're emitting that data by interacting with some sort of an application. So we've got our software engineering friends here. They built some sort of an application. In this case, I have a very simple stack illustrated with Postgres, EC2 instances, Redis, and React. And we have some users that are interacting with that application. They're generating data, right? So the next step, obviously, and this conference is about data engineering, all the interaction data from that is being stored in some sort of a data pipeline. So this is us, right? So this is our part of the puzzle. We're getting the data from that application. We're ingesting it into, let's say, Snowflake. Maybe we're using Airflow for our orchestration. We've got some dbt going on for transformations. So we're doing something with that. And that data is then being used for what? Well, we have some friends on the data science team, and they're consuming data from our pipeline, and they're using it for modeling. Maybe they're building some sort of an ML model that's going to be used in our application. It's going to go back to our users, right? So our users are going to get outputs from that model, maybe because of a cool feature that's built into our app. So this is awesome. We've got this nice circular, sort of pipeline situation going on here. We've got our users, our application, we've got the data pipeline, and then we've got a model that's reading out of the pipeline, going back to our users. Everything looks great. But what happens when something goes wrong in the pipeline? So we've all experienced this. There's some sort of an issue with ingestion, or we have a problem with the transformation job. Our ETL gets disconnected, a token and gets invalidated, something breaks. And now our pipeline is busted. We have a problem maybe with not having data at all. Maybe you have an issue with our data quality. And that goes and impacts the work that our friends on the data science team are doing. And ultimately, that causes a disruption for our users. Maybe this takes the form of like some, obviously wrong or weird predictions in our model. Let's say I'm shopping for some clothing and I get a recommendation for clothes that like obviously don't make sense or don't have anything to do with what else is in my shopping basket. But that creates an issue for our users. Ultimately, it impacts our business. Data science team is upset. They look to us, why is the data busted? We maybe say we don't know, or maybe it was a problem caused by a schema change from our friends in engineering. There's a lot of different places where this could go wrong. But the point is that something broke in our pipeline and it had a bad impact on data science and ultimately on our customers. So this is a pipeline reliability issue or a data quality issue, but either way, how could we start to do something about this? How can we identify these problems and stop them before they make it to our data science team and obviously to our end users? So ideally, we'd want to detect when one of these issues starts happening as early as possible, and we'd want some sort of an alert or a trigger or a way to stop our pipeline, but some sort of a warning to data engineering that something has gone wrong in the pipeline that doesn't rely on getting a report from the data science team or from, obviously a user would be the worst case, right? So how do we get these notifications about something being wrong in the pipeline? Well, let me move our diagram over here on the right, and let's create some space here so we can start to talk about like what's a mechanism that could tell us about a problem in our pipe. And what could go here? What could fill this in? How could we find out about these issues? There's probably a couple different ways to do this. So prior to starting Bigeye, I worked on the data platform team at Uber. And at Uber, I led the team of engineers that developed some of our internal tools for dealing with data management, data operations, data reliability. And in particular, one of the things that we built for the company was a data catalog. So our data science team could go into the catalog, they could look for data they wanted to work with, they could see the lineage of the data, they could see information about the schema, about descriptions, who owns the data, where does it come from. And one of the big tools that was plugged into the catalog was our data quality testing system. So this is how we decided to get these warnings from our pipelines and try to get them in front of data engineers or data scientists as early as possible. Is we'd go and run these pipeline tests. And if we had a failure with a test, we could dump that data into the catalog and get it in front of a user as early as possible. So what you're looking at are screenshots from that testing system, which was super useful and it looked really cool, but there's a big problem with it. So let me zoom in here and see if you can spot the problem. The problem is that each one of these tests required somebody to manually write a condition that would indicate a pipeline problem or a data quality problem. So this might be, an issue that we don't see any new data in the table for, let's say, 12 hours. We expect new data to show up every 3 hours. That could be a test that we would load into our test harness, and that would tell us that our pipeline isn't refreshing on time. We could write a test for having too many null values in a column, and we could write a test that checks referential integrity between two tables. You could write a test for whatever you want, but we'd construct these SQL queries, run them on a schedule. And then when they failed, we'd push a notification about that into the catalog, into the query tool. We could just send an email to somebody on data engineering. But this is a great way to find out about those problems in the pipeline or in our tables. But the issue is exactly what's on your screen here, is that someone had to sit down and write a rule. We had to come up with a manual test that would tell us about one of these failures. And that meant that we had to predict something that would go wrong and write a test case for it, or something would break that we didn't know about, and we'd have to come back in and add a test case for it afterwards. And what this meant is that it was a buildup of a lot of manual labor to predict and anticipate, or to come back in and postmortem and write a test for everything that could go wrong. Now, I mentioned that the title of this talk is Reliable Pipelines and High Quality Data Without the Toil. And that's really what the challenge was. This was a great way to identify problems in the pipeline early, but it produced a huge amount of toil for everybody on data engineering, analytics, and data science, because if you wanted to have a very reliable pipeline or make sure that the data in your pipeline was high quality, we really had to write a lot of these tests and keep them up to date. And I pulled this definition for toil from Google's Site Reliability Engineering Handbook. Google pioneered site reliability engineering, huge contributor to the DevOps movement. But a lot of work that happens that's repetitive, not value additive, and is just scales up with the size of running a service is referred to as toil. And that's exactly what we were experiencing with this testing system at Uber. Is the reliability of your pipelines, the number of pipelines, the number of tests that you had to write scaled up with that as it grew. And it was this very repetitive process of creating all of these data pipeline tests and data quality tests. So is there a better way to do this than writing tests that still lets us find out about these issues in advance? So if we look to tools that are mature and already used in DevOps, on the screen here is Datadog. There's a bunch of other products sort of in this category, but Datadog is a tool used by DevOps teams to also find out about reliability issues with software, with infrastructure. And rather than writing tests, what they do is they monitor what is going on with the behavior of their application or the behavior of their infrastructure, and then they can get alerts about anomalous behavior or issues that might indicate that something is failing. So the great news is that we can take these same concepts and we can apply them in a data engineering context as well. So what that means is data observability. So this is the same phrase that's used in software and infrastructure. Observability, Datadog, Splunk, these types of companies solve that need. We can take those same techniques and we can apply them in data engineering. And what that looks like is a combination of metrics, data lineage, and alerts. Those are the major building blocks of having observability for a data pipeline. So now let's talk about what those different components look like. And let's start with metrics. So what do I mean when I say a metric? And why is this sort of the first fundamental component of having observability for a data pipeline? Well, metrics are attributes of our pipeline or of our data that we can track numerically over time and get a time series out of them. So this first one up top would be the rate of null values in a column measured as a percent. And you can see there, I think this is like the last 30 days or something like that. You can see that we do have some values present in this column, but a lot of the time it's null. Occasionally there's a blip. You can see it drops from 100%, maybe that looks like, 99% or something like that. And then all of a sudden on the right, we have a huge plummet. That column is not null anymore. That means we've got a ton of values suddenly showing up in that column. That could be a good thing. It could be a problem with our pipeline. Not sure. It would depend on the context. But the point is, it's a signal about something going on inside of our pipeline and inside of the data that would tell us that something has changed about its behavior. And that doesn't require writing a test. We can just constantly query the table and collect the percent of null values from it and store that as a time series. So that would be a metric. And in this case, the metric is the percent of null values. Down below, we're looking at freshness. So this is the age of the data in the table. And the reason it looks like this oscillating sawtooth is because as we ping the table and we check when is the most recent row of data written into the table, that's going to climb in age as we get closer and closer to when the next append is going to happen to that table. So we see it gets older and older and older. It goes from near 0 hours old up to about 6 hours old, and then resets back down to 0 as soon as we get fresh data written into the table, because that ETL job ran on a 6-hour schedule. And so we see that this pattern is very stable. So that means that there's nothing wrong with this pipeline. It's running as expected. It's never getting any older than 6 hours old. So these are both different examples of metrics that can tell us either about, the top one is the content of the data. Do we have a lot of nulls, or do we, have values present? So that would be a data quality metric. And then the lower one is the freshness of the data. Is our pipeline running on time? So that would be a metric that we might use for pipeline reliability. So these are two examples of metrics, but there are a lot of different metrics that we could track about our data or about our pipeline. The ones on the left, this is a very interesting set of metrics because these are metrics that can be derived by reading metadata from a lot of common data warehouses. Think like BigQuery or Snowflake or Delta Lake. We can pull this information about all the tables in our warehouse without actually having to run queries on the data itself. We can get these out of logs or metadata that's stored automatically by those data warehouses. So table freshness, the number of rows that we're inserting, or the number of queries that are run on a table, these are all sort of stored for us in the background by default. And so as long as we can access them and turn them into time series, we can get some really useful metrics about the reliability of our pipelines. The metrics on the right, these are a little bit more specific to the data in the tables themselves. So if we want to look at, distribution metrics, if you want to know the max value of a column or the standard deviation of a numeric column, maybe it's a feature that's being used in an ML model. These require direct interrogation of the data set itself. So we need to actually run a query on the data set periodically and collect these metrics back out. But that's really the only way to get information about the contents of the tables themselves. And that's really important in a data quality context. If we're a data science team, we assume that the pipeline is running reliably. If data engineering is taking care of our pipelines, but we really need to know, is the data that's going into our model, let's say we have a training data set, do we have a lot of duplicates in that? Do we have outliers in there? Have we had a sudden shift in a distribution? And those types of metrics really have to be pulled by directly querying the data. But both of these are types of metrics, just about our pipeline, or about the table refresh timings maybe, or about the contents of the table, both metrics. So that's metrics. That's our first big component for achieving data observability without having to write tests. The next piece is data itself. So once we have decided that we want to look into a particular behavior that's been flagged because of a movement in a metric, the next natural thing we want to do is look at the data itself. And so this is the ability for us to grab a sample of data out of the table, or to go and actually look at it. So for example, up top, what you see is a query to fetch data that is relevant to a particular metric. So rather than just doing a select star from a table, if we want to look into why a particular metric moved, we can actually use the metric itself to generate the appropriate sample of data. Example, if we had a metric that is the max value in a column, and we see that that metric has suddenly increased dramatically, what we can do is we can pull only rows of data where the value in that column is above whatever the previous max value was. And so that'll give us a set of data that caused the maximum value to suddenly jump. So this is a great tool for saying, okay, a metric moved, but now I need to understand why that happened. I want to do root cause analysis. So let's go look at specific rows of data that triggered that movement in that metric. Another thing that could be really useful is to just look at the query logs themselves. Now, these are usually stored as tables in the data warehouse, and these QR codes here are links to the specific documentation for each of these three different technologies. Of course, you might be using a different data warehouse. These three are super common, but the docs on each of these pages will tell you about what is stored in the query logs for these tables, and being able to just go and pull up those query logs and see what were the inserts run on a table, what appends were done to a table, what did a user do to a table. That can be really useful as well. But the second component is, now that we know about these movements and behavior in our system, what is the actual data that reflects why that behavioral change happened? And we want to be able to pull the actual raw data up and look at it. Okay, third component, lineage. So in the observability context I mentioned earlier, for DevOps or site reliability engineers, this would be called a trace. They usually refer to metrics, logs, and traces. In our case, we're referring to metrics, data, and lineage, but it's the same idea. It's the set of relationships going on in the system. So in the case of a trace in traditional observability, you'd be looking at calls made maybe between microservices or something like that. In a data engineering context, instead of a trace between services, what we want to look at is the lineage, or the relationship between tables in the pipeline. And that's useful for a couple different things. So here's a picture of what a lineage graph looks like in obviously a very illustrative form. But what we've got is the linkages between all the tables in our pipeline laid out in a visual way. And what that lets us do, for example, is trace a problem upstream in the pipeline from, in this case, we have a dimension customers table all the way at the bottom of the pipeline. We've observed a change in some metrics in that table that's concerning. And what we can see is that we actually have a similar change in the metrics on the company location table, which is the parent of the dimension customers table. And we've also got a change in related metrics on the location table, which is in turn the parent of the company location table. Below, sort of in a faded out view, we've got a few other tables that are also in the parental lineage of the dimension customer table, but we haven't seen any movement in the metrics on those tables. So we can rule them out of our root cause process. So what this allows us to do is say, okay, our metrics have told us that there's a behavioral change in the dimension customers table, but it might actually be caused by a problem in the location table, or a change in the behavior in the location table. So lineage allows us to do this root cause analysis and trace the problem backwards to its source without having to dig through our Airflow jobs or look at our DBT jobs directly in terms of code. We can instead look at it visually as a graph. Another useful way to use lineage in a reliability context or data quality context is to trace a problem down our pipeline as well. So again, we have an issue in our dimension customers table, and we see that that table is a parent for our customer emails table, and we know that that table is ultimately used for some queries that feed a Tableau workbook called Biz Workbook. It's not a great name, but gets the point across. What we can do is we can say, okay, I've identified a problem here in my pipeline. What's going to be affected by that downstream? And that allows us to do things like understand how severe is the problem. If it's on a table, but that table doesn't really go anywhere, if it's not consumed by any analytics tools, then it's probably a low severity issue. We don't necessarily need to wake somebody up. If we know that that is flowing into the training data set for a model, and that model is on an automatic refresh, let's say we have that model retrain, every morning at 2 a.m., and that's a production model that feeds our application. If we have a problem in the dimension customers table, we might need to stop the pipeline, not retrain the model. We might need to wake somebody up. And so understanding what's downstream from a problem that we picked up in our metrics is really important for understanding severity and responding correctly to it. So that's lineage. So that covers metrics, which tells us about behavior in our system, data, which lets us look and introspect into what's causing that behavior, and lineage, which helps us understand where is the problem coming from originally, or where might it be going in our pipeline. The last piece is, how do we pull the attention of our data engineering team to these issues? Obviously, we can't just go and look at our metrics every morning. What if we have a problem happen at 6 o'clock in the evening? What if we have a problem happen at 2 a.m.? So the next piece is alerting. So alerts tell us a metric has moved beyond some certain amount. Therefore, we want to send something into PagerDuty. We want to send something into Slack. We want an email, but we want some way to get the attention of the data engineering team so that we can jump into action. So in a testing context, which is, again, what we tried on my old team, but resulted in a lot of toil, the alerting condition was built into the test. The way that you wrote the test defined, if the nulls exceed 5%, then we should fire an alert. The problem with that is sometimes our data has these sort of like small fluctuations in it. In the example here, we have some nulls, or rather we have some complete values in the column, but not a lot. So we have to choose where to set that threshold. The great thing about observability is that we can use things like anomaly detection instead, and we can use forecasting models. We can learn the behavior of each of our metrics over time, and so we can get more adaptive and smarter alerts that really only pull our attention when necessary and don't require sort of constant manual tuning. So that's a really nice advantage to alerts in an observability context, as opposed to sort of fixed rules in a testing context. So that's metrics, data, lineage, and alerts. So these are the fundamental building blocks of an observability approach to detecting issues in the pipeline itself, or with the data quality of the data moving through the pipeline, without needing to write and constantly update, a corpus of tests. And like I said, this applies both to data engineering, where a lot of times what we really care about is the pipeline reliability. It also applies to data science, though. So we can use observability to understand things like ingestion isn't working, or we have an issue with an Airflow job and it's doing something bad to a pipeline. Tables aren't refreshing on time anymore. We've like tripled the volume in a table because we're doing a Cartesian join, or something weird like that. So that tells us about the behavior of the pipe, which is on data engineering very often what we're responsible for. But then our counterparts in data science, they can use the same techniques for data quality. So they can say, well, I assume that the data is fresh and I assume that the pipeline is running, but they want to know about things, behavioral characteristics inside the data set. So I mentioned distribution shifts. This could be problems with like outliers. Maybe we've got a massive negative value in a column. Maybe that's like a row of test data that somebody inserted and never cleaned up. But if that ends up, being used in a model retrain without us knowing about it, that could impact model performance. problems with formats. Maybe we suddenly change the format of how we're recording a UUID. It doesn't have dashes in it anymore. That might mess something up in a Jupyter notebook. So our data science counterparts can also leverage data observability, but with a focus on the content of the data rather than on the behavior of the pipeline itself, which is more often what we're going to be worried about. So in summary, who's using these techniques for pipeline reliability and data quality? It's a mix. It's both our data engineering team, also our counterparts on data science. How does it work? It works through metrics, data, and lineage, and then, of course, some sort of alerting mechanism to tell us that we have a deviation in a metric that merits attention. And why would we use all of these techniques? Number one, we want fewer outages. We don't want those issues to flow down our pipeline and impact our users. But we also want to reduce toil. We can't spend all of our time writing tests for every different thing that could go wrong in our pipeline or with their data quality. And ultimately, what that leads to is higher reliability of the pipeline and higher quality of the data that's moving through it that is ultimately making its way to our customers or to stakeholders, let's say, executives or product managers or people on marketing who are making decisions with analytics. So that's my talk today about increasing pipeline reliability and quality without the toil. If you have any questions, I'd love to chat. My email is here on the screen, and so is my Twitter handle. Please shoot me a message. I'd love to talk anytime. Thanks for listening to this talk, and I hope you have a great time the rest of the day today at ODSC Data Engineering.